Good morning. Today we're going to go over chapter 4. We're going to go over the first few sections. This video might be a two-parter depending on how long it gets, but I'm going to go ahead and I'm going to get started. We're going to start by talking about solutions and what defines a solution. Now this is of course review from something you guys have seen in the past, but solutions are going to be defined as mixtures of two or more pure substances, and they are homogeneously combined, which means it's difficult to tell that there's more than one part. The solvent is going to be the one that we call present in the largest amount, and the solute is going to be everything else inside of your solution. So then we have to go into what happens to an ionic compound, and a lot of what we deal with today is going to be referencing ionic compounds specifically. When ionic compounds hit their solution or their solvent, they're going to dissociate. Typically, we see this process as dissolving, but dissolving and dissociation are two very different concepts. Dissociation is happening at the molecular level. Dissolving is what's happening at the macro level. So in other words, we can see dissolving, but we can't really see dissociation with our eyes. Dissociation just means that the individual ions are going to break apart. So here we see a picture, and we're going to talk about this one for a few minutes, of a salt crystal that has sodium and chloride ions. And when it gets pulled apart, the water molecules that it's being dissolved into or dissociated into are going to surround in each individual particle as they break off. Now here you can also see the crystal lattice structure of salt, and in this particular case, we're not going to talk too much about salt's structure as far as the crystal lattice is concerned. We're going to come back to that in a future chapter when we talk about molecular bonding and all of that lovely stuff. But for now, what we're looking at is the crystal lattice structure of a salt cube that's being pulled apart at the molecular level by water molecules. The process of pulling those things off and making them surrounded by water molecules is referred to as dissociation. Now there's some other types of things we want to talk about in this particular vein. The first one being that if it's an electrolyte, so if a compound is considered an electrolyte, once it dissociates, it would also dissociate into positive and negative ions. Those positive and negative ions being present would allow for that electrolyte solution to conduct electricity, and that's one of the major concepts in this particular first section of your reading. So an electrolyte is going to be one compound that is made up of ions that, when it's dissociated, leaves behind positive and negatives in its solution. So from there, we can talk about an electrolyte versus a non-electrolyte. An electrolyte is going to be one, like we said, that dissolves into ions or dissociates into ions. And a non-electrolyte is going to be one that does not dissociate into ions. In other words, when you put it into water, it will dissolve but not dissociate. In other words, we might see it disappear in water or in any other solvent, but we will not see it conduct electricity, and it will not break apart at the molecular level, which is really the difference between an electrolyte and a non-electrolyte. From there, we just have some kind of summary stuff. We've talked about the ionic version of electrolytes. Molecular versions of electrolytes tend to be a lot of different things. Most of them are non-electrolytes. In fact, most ionic compounds, all ionic compounds are electrolytes, because the term ionic means able to dissociate. So molecular compounds are going to be the ones we want to worry about. Think sugar, think big proteins. Those things don't break apart when they hit water. If they did, we wouldn't be able to use them on a molecular level or in our body for digestion and all of that lovely stuff. As far as these types of compounds are concerned. Another thing that we want to talk about is how molecular compounds tend to be non-electrolytes, with two major exceptions, and that is acids and bases. And we will wrap up our discussion today by looking at some different acids and bases and basic information about those types of compounds. From there, remember that one of the major differences between an electrolyte and a non-electrolyte, and here we see our example of pure water, sucrose solution, so sugar, and sodium chloride. We define an electrolyte by whether or not it can actually light the light bulb, aka conduct electricity. So if it cannot conduct electricity, it must mean there is no ionic compound present, or that there are no ions present. And sometimes when we put our tap water in a beaker, if we have enough ions in that water, which we add ions to our water, A, to keep it healthy, and B, to treat it for bacteria and make sure that it's safe to drink, anytime that we do that kind of thing, sometimes we will get some minerals left over in our water and or ions left over in our water. Very unharmful, no issue there. But here we see an example of pure water, which is not the same idea. Pure water has been filtered and or sorry, I'm blanking on the word, distilled, that's the word, to remove ions specifically. We use pure water in certain aspects of chemistry, and we will this year. I'll go and I'll get distilled water, and we'll use it for specific experiments. So keep in mind there is a difference between pure water and the water that you're used to drinking. A lot of your water has electrolytes added to it for various purposes, taste, and or other nutrients. A strong electrolyte and a weak electrolyte. We do not see an example of a weak electrolyte here. We only see a strong electrolyte. A weak electrolyte is one that we're going to come across many times when we get towards our acid-bases chapter next semester. But a weak electrolyte is only going to partially dissolve, which means it would very dimly light the light bulb in this particular example. Okay? So strong electrolytes are going to be strong acids, strong bases, because when they hit water, they will dissociate completely. Strong electrolytes are also going to be ionic compounds, which is not on here, but for now we're focusing on the acid bases part of this. We're looking at not only are we seeing some ionic compounds like hydrochloric acid and hydrobromic acid and hydriodic acid. These are all ionic because when they dissolve, they definitely leave behind those ions. We're also seeing some molecular versions of acids because when they dissolve, they leave behind larger ions. You know what? I think that's wrong. Actually, these are all ionic. Yeah, these are all polyatomic ions, right? When we say molecular acids, I don't have an example of a molecular acid on here. A lot of times molecular acids are very large and not very commonly used in bench chemistry. So these are all of the strong acids and bases. What I want you to do with these is I want you to memorize these. And remember, we talked about this last week where I said I was going to make you memorize these. Now, remember that some of these are going to be ones you've already memorized as far as polyatomic ions. There are a couple that are not necessarily easier to memorize, but please just, try to commit these to memory. One reason I want you to do that is because if I say hydrochloric acid, I'm expecting you to be able to know that that's HCl. Or if I say nitric acid, I'm expecting you to know that that's HNO3, and so on and so forth. For the bases, it's actually a lot easier than it seems. You're looking at group 1 metals that are bound to hydroxides, or you're looking at group 2 metals bound to hydroxides. And there are only a few group 2 metals for you to memorize, but all of the group 1 metals are up here. Okay? So, that being said, for strong bases in this particular definition, and there are other ones and we'll talk about them, for strong bases in this definition, we're really just focusing on these two definitions. All right, next up is going to be soluble ionic salts, like we just said, NaCl. We're going to see calcium carbonate, which is one of those soluble ionic salts. Anything that has a positive and a negative is going to be considered an ionic salt. Types of reactions were discussed in this next section, and a few of them were referred to slightly differently than you've seen in the past, like metathesis reactions and precipitation reactions. Please don't freak out. Metathesis was just a fancy term for exchange, and we learned about two different types of exchanges. This is where single displacement and double displacement are going to fall in our previous definitions. Another type of reaction, which is a type of double displacement, for the most part, is a precipitation reaction. And what happens is, when we take two soluble compounds and we add them together, if a solid forms, we now have to refer to that as a precipitation reaction. That precipitate that gets formed is one that we are going to work on predicting its formation. And in order to do that, we have to figure out what is insoluble and what is soluble. First, let's talk about how to actually do a metathesis reaction. And this is the big difference from last year and one of the major new concepts in chapter 4. I'm going to ask you to predict what happens when these two things add together. And you know that these two things, just looking at them, each have two parts. You've got the positive metal, so in this case we have Ag, and the positive metal, in this case we have K. We also know what their charges are based on what they are attached to. In this case, We know nitrate is in -1. Remember, that's one of your common polyatomic ions. We know chloride is in -1 based on its location in group 17 with the other halogens. And because of those two charges, we also know that silver and potassium are both going to be +1. So in order to predict our outcome, we know they're going to switch places. That's like our first thing. We know they're going to switch places. So now the potassium is going to go with our nitrate, and our silver is going to go with our chloride. And since they were +1, -1, +1, -1, in these types of reactions, the charges stay the same. So we know that this is still going to be a +1 and this is going to be a -1, hence there's no subscripts. We know this is going to be a +1, this is going to be a -1. So a very basic example, and if we look at it, of course that's what we see. Now, one of the things that we can take this and do a step further is we can predict, because this is a metathesis reaction, which of the two is going to be the precipitate in this type of equation. So the next thing to talk about is, how do we know that the AgCl is going to be the solid? How do we know that the potassium nitrate is going to be still soluble? In a precipitation reaction, okay, there are a few things that must be true. The first thing that must be true is both reactants must soluble. This means aqueous, okay? So they should have an aqueous symbol after. That's the very first rule. Both reactants must be soluble. Number 2, bear with me. The next one is one product must be soluble. Again, AQ. Okay? Now, the last rule in a precipitation specific, meaning a solid is formed, is that one of the products must also be, one product must be a solid. Okay? In other words, we have to figure out what thing is the precipitant. We're going to look at the solubility rules for this particular reason. In solution chemistry, we have to be able to predict that solubility by knowing what is actually already in the mixture. Remember that in specific precipitation reactions, which is what we're talking about at this moment, one of the products must be a solid. Every other species must be aqueous is the rule, okay? So here we have the solubility guidelines. And in these guidelines, we're going to see ways of figuring out if something is soluble, aka aqueous, with exceptions to those rules, and or something that is solid. No, it's soluble up here. Ah! Sorry. Using my husband's tablet. Not my typical jam, but I can write on it, so that's nice. All right, so the solids are going to have rules, right? So here's the rule. And we're breaking this down for a reason. You're going to want to make sure you understand how to read this table. You will always be given this table. So number one thing, you do not memorize this. There are some that will naturally happen in your brain. Like for instance, you'll quickly realize that these two are very, very convenient to just know off the top of your head, aka that all nitrates are soluble, there are no exceptions, and all acetates are soluble, no exceptions. So there are some that you will pick up naturally, but for now, we want to make sure we know how to read this table, because I would always give you this. Now, if you're planning on taking the AP test, they don't give you this, but the amount of time or the amount of questions, I guess, that would contain a solubility question is going to be less than 2%. So memorizing the table really isn't that useful even for the AP test. But for me, I need you to learn to read this table, not memorize it. Okay, so let's practice. And I'm going to bring up your, I'm going to write out what I gave you for your daily Q today so that we can go through that. And we're going to use this table to predict whether it's soluble or insoluble. All right, so compound number 1 was barium nitrate. Okay, so in order to figure out if this is soluble or insoluble, we're going to look for the anion first. That is one of the first things you should always do. Look for anion of the ionic compound. It's really the only rule is look for the ionic compound's anion. The compound that, because that is how it is listed on the rule, is by anion or polyatomic ion. So for this particular one, we've got nitrate. Nitrate is, of course, the top. We just talked about this. It is one of the always soluble, no exceptions. So this is going to be soluble. Doesn't matter what's attached to it, it's soluble. All right, next up is potassium sulfate. Okay, so we're going to look up again by the anion sulfate, which is on the bottom of my soluble part of the table, and it says that all compounds containing sulfate are soluble, with the exceptions of these 4 metals being attached. Now, potassium is not one of the 4 metals, so it does not fall under an exception to the solubility rule, which means that it must be soluble, due to the fact that all sulfates are soluble and potassium is not one of the exceptions. All right, let's look at C. I'm going to erase this one. Our next compound from our daily Q was barium sulfate. Okay, so again, I'm looking at the sulfate, and I'm looking to see if any of the ones that I had are going to be an exception. In this case, yeah, looks like barium is one of the exceptions. Because it's listed as an exception to a solubility rule, then we are going to say that this one must be insoluble. We really haven't worked on the bottom of the table, so I'll give a couple of examples of stuff on the bottom of the table here in a second. All right, and the last one from your daily Q was potassium chloride. Again, I'm looking for the Cl ion. I see it here. The exceptions are not going to include potassium, so this one is, of course, soluble. All right. Okay, so let's do a couple more. You got to get used to using the table, because once you can predict the things that are going to be formed, the next step is to identify which one's going to be a solid before you can move on to net ionic equations, which is our next major topic. All right, so let's do NH4OH. Okay, so here we go. Again, we're going to look for the anion, and these, of course, are both polyatomic ions. The anion is going to be hydroxide, and this is the insolubility rule technically, but since I've got hydroxide here, it says all hydroxides are insoluble. Now let's look at the exceptions to make sure ours isn't one of them, and look at that. It says that ammonium, which is our ion, our cation, is one of the exceptions. So since all hydroxides are insoluble, but ammonium is one of the exceptions, that means this is soluble. Okay, I'm hoping this kind of helps you see what you're supposed to be doing. I'm going to stop this video here, and I'm going to upload a second one here in a little bit, but I'm going to continue our lecture with net ionic equations next. Okay, so bear with me, guys. We're going to do 2 parts. The longer they get, the harder they are to upload.